In this module, I have developed a R case study on vector autoregression model. Here I took a real life data from the Montgomery time series analysis book. That data I used to demonstrate the analysis. First, I explored the data through exploratory analysis to identify the appropriate order of the model, through ACF, that autocorrelation function plot, and then the cross correlation function plot that helps to identify whether any cross correlation exists between two endogenous variables or not. And then finally, I will show you, how to identify the appropriate order of the vector autoregression model, and after fitting the model, then I will show you how to identify how to check the validity of the model based on regression diagnostics with respect to different diagnostic plots that I am going to show you how to generate those and separate those from the actual R objects. So here mainly the package that I am using for, there are several packages, but here I am going to use the VARS package from R to demonstrate this particular case study. Let's focus on the presentation of vector autoregression model. The main outlines that I am going to cover here, as I mentioned, the exploratory plot related to the vector autoregression, the selection of model by ACF and cross correlation, the fit a VAR model that is the vector autoregression model by VARS package available in R, and diagnostic plot and the test for VAR models. The first exploratory analysis starts always with time series data. Whenever you have a time series plot, whenever you have a time series data, that can be done by a simple plot of the time series. Data was stored in data.csv, and this data is actually taken from a book that is called Montgomery book for time series analysis. It is a chapter for multivariate time series analysis. You will get this data. Data has a two components of two parameters. The pressure measured at the front of a furnace and the pressure measured at the end of the furnace, that is I indicated here as front and back. Front is the front of a furnace and pressure back is the pressure measured at the back of the furnace. So this is the two variables in a data set that we have. The data is available, full data is available in that book, the Montgomery time series analysis. And that if you can just have a time series plot, what I wanted to do here, I wanted to plot both the series in a single axis. So I use a plot function and then I use a line function to superimpose the plot over the same axis. So that will generate the time series plot, the blue indicating the black and red indicating the front pressure of the furnace. Next, I'll explore the autocorrelation function of the data. Again, here I wanted to put both the ACF of the front pressure and ACF of the back pressure together. So I use the pair function and MA flow C equals 1 to 2. So I wanted to create 1 by 2 row, and that will give you two plots together in a single, two panels in a single plot, where the width data, width can be used as a function. Width is a function, that means with the data you are using this function. So if you use width function, you do not need to write data $pressure underscore front. So just avoid this. I just use the function width data, and width for front and width for back with data and ACF. For that ACF function just need to pass within the width function, start with the data. And then if you see the ACF plot for pressure at the front and pressure at the end of the furnace, you will see some exponential decay. This exponential decay indicates that maybe the VAR model be the appropriate choice for this particular data. But one more thing that you need to explore, that the pressure might have some cross correlation. So we need to explore the possibility of cross correlation, and for that and to select the appropriate model, an approach to model identification would be to fit the ARIMA models to individual time series and consider the cross correlation of the residual. So as I mentioning, so the appropriate choice of the model would be based on the cross correlation. To get the cross correlation, it's just like ACF, PHCF. You will have another function exists in R is CCF. CCF is the cross correlation function. That CCF function can be used to draw the cross correlation for the pressure at the front of the furnace and pressure at the back of the furnace, and can be compared. So for cross correlation, again I wanted to put both the cross correlation plot together with the pressure front at the pressure at front of the furnace and pressure at end of the or back of the furnace, and together. For that I use with data, then CCF function. CCF function is the cross correlation function, and pressure underscore front, pressure comma pressure underscore back. I mean here actually syntax is x comma y, the first variable, second variable, and then lag, maximum lag that you want to look for. So I set here 30 and y lab equals to cross correlation, and main as the title of the plot I mentioned front versus back. Then the next plot is the pressure front residual. So the residual plot, to get the residual plot, I fitted the auto regression model, that means AR1 model of the front. All I put together here might be little difficult for you to understand. Let me explain one by one. First, I fitted a AR1 model for pressure underscore front, that is the AR corresponding AR, this particular this AR pressure underscore front. This function will feed the AR model with order 1, and dollar reside will give the residual of that particular fit corresponding to the pressure at front. Similarly, the AR model with AR order 1 was fitted for pressure at back of the furnace, and then the residual was derived with the dollar RESID. That if you use that, that means the AR object itself stored the residual by default. So you just need to extract the residual after fitting the AR. So AR from the AR object. So these are the first steps that I did to feed the AR of order 1 for both the variable, and then I extracted the residual from both the objects generated by AR function, and then that residual was passed within CCF function, that is cross correlation function, and then I set the lag maximum as usual before like before 30. And in this data there are some not available was there, so I used na.action equals to na.pass, and that ylab equals to cross correlation and mean RESI front versus RESI means is residual back. So with this function, then I set the plot again 1 by 1. I set as 1 by 2 by MF row C1, 2, and here I set back to FF row 1, 1, and that will generate the two plots. I mean, if you just see both the plots of ACF, PACF and the plot for this cross correlation, it is suggesting that vector autoregression of order 1 or vector autoregression of order 2 might be good choice, because there is a strong evidence of cross correlations. So as there is a strong evidence of cross correlations, so you should consider the vector autoregression, because two variables are dependent to each other. So that's why VAR1 or VAR2 might be the appropriate choice in this context. So let's look how to feed the the vector autoregression of order 1 feed, but I am here showing because data is preferring 1 or 2, so I am here showing 1, and you can try with many other orders with even not only here I use only 2 variables, you can use more than 2 variables for your purpose. For that you have to install the package called VARS, VARS, all are lowercase. So you have to install the package VARS. If it's available, then you just load the library VARS, and there is a function called VAR, as you know, V for vector, A for auto, R for regression. So VAR function can be used to generate the VAR fit results. So it's quite simple. The data that you have to just provide a data frame or a matrix of all the endogenous variables. Here there are 2 variables that is stored in second and third column of the data. So that's why I use 2, 3, that is second and third column. Combining this, either it has to be either a data frame or a matrix. So I fitted for 2 columns, so you can look for more than 2 columns. There just the data frame, you just construct a data frame or a matrix of, say, if you have in data and 5 endogenous variable, then it would be n by 5 matrix or data frame that can be passed within VAR function, and then P here stand for the order of VAR. So order of VAR, I took 1, so P equals to 1 and type equals to both, or by default you can choose. That will generate the results. So if you just type feed VAR1, it will give you estimates of coefficients corresponding to both the variable. Say the first one, if you see the first one corresponding to the pressure front, and second one corresponding to the pressure back, so these are the coefficients that can be estimated by the VAR functions. So it will be just the estimate of the point estimation of the regression, the vector autoregression parameters, but the summary can be generated either together or by separately. If you just want to generate the summary separately, summary will include details results of all, including the different tests, and tests for the coefficients as well as tests for other diagnostics procedures. And say you can just write summary, and feed VAR1, it is the object that I created for that VAR object. So feed VAR1 can be passed through this, and then you can write equation equals to the pressure underscore front. The equation means which endogenous, the equation corresponding to which endogenous variable. Here it could be any order you can follow, but just as you are mentioning the name of the variable, that's it. So here the name of the variable was the data frame that I passed through is the pressure underscore front. So you just have to mention the pressure underscore front for the equation. That means the equation is telling that the equation, the summary of the equation corresponding to the pressure underscore front, and that will generate all the results from all endogenous variable. If you see the variable results indicating the endogenous variable as pressure front and pressure back, the deterministic variable both, then sample size is 185, log likelihood is this, root of the characteristics polynomial is given here, and this is the model that I fit, and then this is the basic description of the model that was fitted, and the next information that they gives is the equation, the estimate of the parameters corresponding to the equation that I mentioned. I mentioned here the pressure underscore front. So this is the pressure underscore front. So that is the coefficients are given here from 10, constant, and the two coefficients of VAR, that is front and back one, that is given here, and the t statistics, t value for corresponding to t statistics are provided here, and the p value is indicating here. P value is showing except train, all other coefficient corresponding to other variables are significant. And then here is you will have a residual error and this degrees of freedom. The multiple R square also provided as 0.7909 and adjusted R square is 0.78. So that means almost 78 to 79% variation can be explained by this particular model, this particular the model that we fit. And then if you just looking for the other variance covariance correlation matrix, and the correlation between pressure and back also is reported here is 0.51, and covariance of the residual also provided here. So similarly you can call for the other variable, that is pressure underscore back. So pressure underscore, that means pressure at back of the furnace, that also can be generated. It will provide you the initially the same information that you have common for all, that is the basic descriptive of the model. This is common for, if you just call together without mentioning the which equation you are looking for, just summary feed var 1, it will the ones it will give, and then the same thing corresponding to the equation would be provided separately together. So just because it might take bigger space, so that's why I didn't show all together. I just splitted the summary for different variables one by one. And sometimes what happens, you may have more than 2 endogenous variables. Sometimes it could be 5, 6, 7 endogenous variables. In that case, it's really hard to display. So it is better always the call equation by the summary for equation that of you are interested to look for one at a time. So here similarly all the coefficients are here. Again, trend is not significant for this, but other coefficients are significant. R square is quite small compared to the pressure at front of the furnace. So here R square of this model mention around 46% to 45%. That means 45% to 46%. Rather, I can consider as a 46%. Yes, 46% variation can be explained by this particular vector autoregression model that I chose for this particular variable. And it also provides the the same covariance matrix and the correlation matrix. Variation is normal, and whereas the next panel you can see the residual plot. This is the residual plot, and residual plot is showing no pattern, so it is distributed uniformly over 0 line. The other two plots that are indicating here, the ACF of the residual and PACF of the residuals. So ACF and PACF both indicating no significant autocorrelation exists in the residuals. That indicates the fit is quite good. Similarly, you can use get the diagnostic plot for the pressure at back of the furnace. Now, if you compare the first plot, the fitted and the raw data plot time series plot, then easily you can see the fitting was much better in the front pressure than the back pressure. So it's quite normal. That was clearly explained by the R square was quite low compared to the R square for pressure back was quite low compared to the pressure at the front of the furnace. And similarly ACF and PACF also not showing much of the 1 or 2 is too far, this is not that much significant. So I don't see any significant evidence of autocorrelation in the residual of the model. You also can test in this function. There are few diagnostic test functions available. So you can test for serial correlation. That can be done by serial.test function that is available in this VARs package, where the feed var1 has to be passed through serial, and then lag points you need to mention, and the type of type need to mention as PT dot asymptotic type is the one type for the stress statistics is a default, but I mentioned this. But you can, for further help, you can get the help of serial.test. All the other options are available. You can choose whichever choose for. So here it is telling it is not significant at all. So serial correlation is not significant because this is for the residual. So that we also observe in the residual plot ACF and PACF that there is no evidence of autocorrelation. So quite normal that it should be insignificant. You also can perform the normality test. For normality test, it is normality.test. Again, you have to pass the feed var1 object, that the var object within the normality test. That will give you the normality test. The first one is the JB test, that is also insignificant. The skewness also showing insignificant. The kurtosis also showing insignificant, and that indicates that the data can. In this module, we took a real life data and we learned how to fit a vector autoregression model by R package VARs, where the function was var uppercase VAR, and using we also learned how to select the appropriate order of the VARs through the ACF and CCF function, and then finally we feed the this particular model, and we also saw the different diagnostics plots to check the validity, and also we performed some diagnostic test in this module, and hopefully after completion of this module people would be able to analyze any data related to vector autoregression model.